All right, friends, welcome back. In this video, I'd like to go ahead and cover section 3.4 from your textbook and take a first day for this. In this video, specifically, we're going to be talking about a strategy that you can take to find the zeros of a polynomial function if that polynomial function does not really play nicely with any of your strategies that you have been using previously, right? So let's say your polynomial does not factor, or maybe it's not a quadratic that we have all these tools to solve and find the zeros for. We're going to take a look at a couple of different examples of polynomial functions today and learn how to find their zeros, okay? So it's a little bit of a process, and that process is going to be something that we are going to be able to do because of a couple of useful theorems in the world of algebra, okay? So that first theorem is something that we call the rational root theorem, and basically it's going to say that if you have a polynomial function, then every rational root, and keep in mind what rational means, that just means that you can write it as a fraction, okay? So all of the roots that you could write as a fraction have the form which is given here, right? So this fraction of something over something else, p over q, in all cases, those fractions are going to look like fractions that are made with a number that is a constant of your, a factor of your constant term on top over a factor of your leading coefficient on bottom, okay? So just kind of explain what that means. If I have a polynomial that looks like this, say like 64x to the third plus 152x squared minus 62x minus 105, that is not something that we can factor using any of the tools that we've had previously, so we're going to have to do this new method for being able to find its zero. So you see me here setting this equal to 0 because that's what a zero is. It's a special input that makes the function output a 0. And I've already done the heavy lifting here, and you can see here that you have these three zeros of the function right here, okay? Now, something particularly nice about these zeros is that they follow that pattern that we said from the rational root theorem, okay? All these numbers that are on top, these numbers that look like 5 and 3 and 7, these are all factors of your constant, which is negative 105, okay? These are all numbers that go into negative 105 nice and evenly, okay? These other numbers that are on bottom, the 2, the 4, and the 8, these are all factors of your leading coefficient, which here is going to be 64, okay? And so these are the special inputs that if you plug them into these machines, it would output a 0, and we could see that it follows that same general pattern according to the rational root theorem, okay? Now, we're going to be using that theorem as we go through and solve some problems here in this lesson. We have some other theorems that are pretty useful for being able to describe what we should expect at the end of our process here, right? So the first one is called Descartes' rule of signs. It's named after French mathematician René Descartes. He's the guy that came up with the XY plane, fun fact. But he also came up with this rule of signs. And basically, this is going to tell you how many of your roots of your polynomial are going to be positive and how many are going to be negative, okay? And so you could read through this theorem here. Basically, you're counting the sign changes in f of x, and then you're going through and counting the sign changes in f of negative x. And that's going to be the number of positive roots or the number of negative roots, okay? You also see this extra little bit that's tacked on here, so it's either going to be that number or less than that number by some sort of even, okay? So in the case right here where you count 2 sign changes, the number of positive roots we would expect is either going to be that number 2 or less than that by some sort of even number. So it's either going to be 2 positives or less than 2 by some sort of even number. So 2 or 0 in this case, okay? And moving on to the case where you're counting the number of negatives, you do have to figure out what f of negative x is, and that's what this is right here. An easy way to think about that, folks, would be if you plug in a negative x everywhere that you see an x, basically the sign is going to change on all the terms with an odd exponent, okay? So 5 is odd, so its sign is going to change to a plus. This over here, that is a exponent of 1. That's odd, so its sign is going to change. All of these signs are all these signs of terms that have an even exponent on it, like say here the 2, and then even your constant term, because remember that's x to the 0 power. 0 is an even number, okay? All of those signs are going to stay the exact same. So it's basically going to be this negative that changes to a positive, and this positive that changes to a negative, which you can see happens right over here. And then you just do the same thing. You count the number of sign changes. Here that's going to be 1, so the number of negative roots that I would expect is just going to be that number or less than that by some sort of even number, okay? So that's what Descartes' rule of signs says. Again, it doesn't really tell you what the zeros are. It's just going to tell you how many of them are going to be positive and how many are negative. This last theorem that I want to take a look at is something called the fundamental theorem of algebra, which actually the statement of that is in the quotation marks there. But what this leads to is what we call in math a corollary. It's a direct consequence to a theorem, okay? And that's going to be this. It says that a polynomial function will have, at most, as many roots as its degree, okay? And so what that means is that you're never going to have a number of roots that is more than the degree of the function, okay? So take for an easy example like f of x is equal to x squared. That's a polynomial. It has a degree 2 because of that exponent of 2, and you guys know that that makes a parabola. Well, I'm not going to have a number of times I cross the x-axis to be more than 2, right? I'm either going to cross no times, it's not going to touch the x-axis at all, or maybe it just swoops down and kisses the x-axis and then swoops up. That would be 1, 0, or x-intercept, or maybe the parabola crosses twice, okay? At most, that would be 2 times that I cross the x-axis, which is where we get this nice theorem from, okay? And so, if we put all of this together, what it basically gives us the ability to do is it gives us the ability to find all the zeros of a polynomial that we might be given by listing out the rational zeros or the rational solutions. And so here's a quick step-by-step for doing that. I'll be honest with you, doing these first 2 steps is going to be less important in some examples than it will be for others. So we'll go through and do that step, but for the most part, it's going to be this last 3 steps here that is going to be where we're actually digging deep and finding the actual numbers here. So I just want to go ahead and explain that process by doing an example. You can see that I've got all the steps here listed out. So here is your first example. So we have f of x is equal to 2x to the third plus x squared minus 4x minus 3. Real quick, before we get into this process, I just want you to pause and just ask yourself, if you walked up to this problem just on your own and you remember all of your factoring skills from section P.4, then you might be tempted to factor this by grouping because it has 4 terms in it, right? So if we factor this by grouping, we group together the first 2 and the second 2. That first group has a GCF of x squared, which we can pull out, leaves behind 2x plus 1. And then that second group has a GCF of negative 1 we could pull out, it leaves behind 4x plus 3. And that creates a problem here for us, right? Because when we factor by grouping, we really wanted those leftovers to be identical so we could factor those leftovers out of both groups, and that would create a factorization for us. But we notice here that these are not identical at all, so factoring by grouping is not going to work out here for us, which is why we need this new method, okay? And so here in the video, let's go ahead and go through this process here. So number 1, it says use the fundamental theorem of algebra to get a total number of solutions. The degree of this polynomial is 3. You can see that this is already written in standard form, and the largest exponent on an x is a 3. And so that's the degree. That's going to be a degree 3 polynomial, aka a cubic polynomial. And so what we might say here, according to that corollary from the fundamental theorem of algebra, is that we would expect to have at most 3 zeros. Okay? Again, doing that question is not really something that helps us find those zeros. It just kind of gives us an idea of how many we should expect. Okay? And Descartes' rule of signs here says to determine the number of positive and negative solutions, we're just doing the sign changes for that. So if you go to the original f of x, I start off with a positive 2, and then I go to something positive. That's not a sign change. But then I go from something positive to something negative. So that's one sign change there. And then if I go from something negative to, again, staying negative, that's not a sign change. So I'm only counting one sign change there, which means that's the number of positive roots that I would expect here, okay? As far as the number of negative roots, remember you're doing the sign changes at f of negative x, which means you're going to go through all of the terms, and every single one of them with an odd exponent, you're going to change its sign, okay? So we're going to go ahead and pick up here with a negative 2x to the third, because that 3 is an odd number. The next term, that's x squared. 2 is an even number, so we're going to keep that sign the same. The next term, that's 4x to the first, so that's an odd number, so we're going to change its sign to a positive. And then finally, that constant is always going to be considered to be a term with an even exponent. So let's count the number of sign changes here. If you're looking here, I count, here is one of them. So that's one sign change going from negative to positive. And then if you read throughout the rest of it, I see another one. Okay, so that's going to be another sign change that we're going to have here. So as far as the number of positive and negative zeros, we'll just go ahead and write these down here. Okay. We would expect, according to Descartes' rule of signs, to, in terms of the positive sense, I would just expect one of them to be positive. In terms of the negative sense, I would expect 2 or less than that by some sort of even number, so 2 or 0, okay? So again, doing those first 2 steps doesn't really get you any closer to figuring out what the zeros are. They are just preliminary steps that just kind of help you understand or see if your final answers are actually going to fit these descriptions and just kind of check in with yourself. Like, yeah, this seems correct according to what I talked about before, right? So now let's actually go through and actually talk about that process here. So it says in step 3, use the rational zero theorem or the rational root theorem to list all possible rational solutions. Okay, so let's pick up with that process here, right? So if you read through that theorem again, we're going to be creating a bunch of fractions here, and those fractions are going to be made by taking a look at factors of our constant term, which if you read up above, our constant term was a -3, so we're looking for factors of -3 over factors of the leading coefficient, which if you look up above, the leading coefficient there is just simply a 2. We're looking at the original f of x, not f of -x, okay? And so now we just need to brainstorm on the factors of these numbers. And in this example, it's nice and easy because numbers like 2 and -3, these are prime numbers, okay? So these are numbers that only 1 and themselves go into these numbers, right? So the positive and negative versions of these numbers are going to be something that we're going to have to keep track of. So I'm going to say that positive and -1 go into -3, and also positive and -3 also go into -3. Okay, so those are all the different factors of -3. We're going to go ahead and put those numbers in the top and then do all the combinations with all the numbers on bottom, which are going to be the factors of 2, which is positive or -1 and then positive or -2. Okay. If we had bigger numbers than these that might have more factors, we would have to consider those factors, and we'll see that in the next example that we do, okay? Now, what we're going to now do is we're going to create a bunch of fractions with a number from on top over a number from on bottom. We're going to have to do all the combinations, okay? Well, in this first case, what I might go ahead and consider doing is just the case where I have that plus or minus 1 on the bottom, okay? And then doing all the combinations of numbers on top with that 1 on the bottom. Well, if I have a 1 on bottom, then that's not going to really change anything, right? So that's just going to be positive or -1 and positive or -3 to start us off. And then I'll go ahead and consider, what if 2 is in the bottom, okay? Well, numbers on top over that 2, that would look like positive or -1 over 2, and then positive or -3 over 2. And we're just going to leave those as fractions just like that. But again, what we're doing is we're coming up with all the different possibilities for a number on top over a number on bottom. And what this does, folks, is this creates for us a nice pool of applicants to the job that you're hiring for, right? That job being a 0 of the polynomial, okay? And so if you look carefully, that's actually 8 different applicants applying for your job, because you have the positive version of these 4 numbers, and then also separately you have the negative versions of these 4 numbers. So that's 8 total, okay? We're now going to go ahead and actually start that interview process and figuring out which one of these candidates actually gets the job, and that's going to be done by moving on to step 4, which says use synthetic division to test each of these rational solutions from step 3. And what we're looking for is this. We are looking for which one of those after synthetic division is going to give us a remainder of 0, okay? And so I'm just going to go ahead and start fresh in my list, positive 1, let's say we'll start with here. So we're just going to go ahead and use positive 1 with synthetic division, putting that in my little corner box. And then, of course, we want to go through on our original f of x and then just borrow all the coefficients of that, right? So I've got 2, positive 1, -4, and -3. So setting this up, remember that positive 1 is going to get the job if, after doing synthetic division, we end up with a remainder of 0. So since that's what I want to end up with, I'm just going to put that there and see if that gives us what we want. Okay, so going through the synthetic division, drop the 2, and then multiply, and then add, multiply, and then add, and then multiply, and we arrive here at this problem, right? So -3 plus -1 is not equal to 0. So what that means is that positive 1 does not get the job, okay? So we're going to move on in our list. Positive 1 didn't get it, but what about -1? That'll be the next one on our list to test here. So let's try that, right? So drop a 2, multiply, and add, multiply, and then add, and then multiply, and looky there, okay? So yeah, -3 plus positive 3 does give us 0. And so what that means, of course, is that -1 is going to be one of our applicants that actually is going to get the job, okay? And that job, again, being a 0 of my polynomial, okay? So if -1 gives us a remainder of 0, which it does, then that automatically means that it's a 0 of my polynomial, okay? It may not be the only one here, so I'll just say comma, ... There could be others. But where we pick up from here is we just go ahead and write this out in its factored form, because if I know that -1 is a 0 of my polynomial, that corresponds to an algebraic factor that looks like x plus 1, okay? Now, that would be x plus 1 times something else, and if you're asking yourself what that something else is, then you don't need to look any further than just what the quotient of your synthetic division was over here, okay? So remember how we interpret this. This would be that middle number is our x term, and then that first number would be our x squared term. So cleaning that up a little bit, we would have a 2x squared minus x minus 3, and that would be exactly what goes over here, 2x squared minus x minus 3, okay? So all these other zeros here, the dot, 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 that will be what we get whenever we continue to factor what we've got here and then set it equal to 0 and solve, which is actually step 5. So step 5 says to finish up for the factoring. So at this point, we've got f of x is equal to x plus 1 times 2x squared minus x minus 3. We're just going to continue to factor this by going back to our section P.4 notes and remembering how we might factor a trinomial like this, okay? I'm not going to focus on the steps to actually go ahead and do that because you guys can go ahead and watch that in your P.4 video, but I will share with you that when you do that, you're going to end up with x plus 1 times 2x minus 3 whenever you factor that up, okay? In which case, you may notice now that you've got 2 copies of x plus 1 in the factorization, and so we can further simplify this and say x plus 1 squared times 2x minus 3, okay? And that would be a complete factorization for this polynomial f of x that we started with initially, okay? And so now what we want to do is we finish the factoring. We now want to just go ahead and set this equal to 0 and solve. So I'm going to take out the f of x and replace it with 0, and then we're going to go ahead and use that 0 product property to get the rest of our zeros here, okay? When we set that first quantity equal to 0 and we solve, we're going to get the 0 that we already knew about. We're going to get x is equal to negative 1. We knew about that from step number 4 when we listed out our zeros, so that's pretty good. When we set this other factor equal to 0 and solve, we're going to get x is equal to 3 over 2, which is another candidate that was in our pool of candidates from before. We had 3 over 2 in the very beginning up there, okay? So what that means, folks, is that for some problems, the ones that only have real zeros, you can go ahead and do this problem by going through the synthetic division for each one of those 8 candidates and seeing which ones give you a remainder of 0. I would encourage you to not do that, though, because you may miss out on some complex zeros, and so doing it in the process that I'm demonstrating here is probably the best probably going to be the best way to do it, right? So I'm just going to go ahead and write my final answer by listing out a complete list of zeros here. So we ended up with x is equal to negative 1, and then we just found x is equal to 3 over 2, and that will do it for us here in this problem, okay? And so, again, the goal is if I give you a polynomial function, can you find all of its zeros using this new method, okay? And this new method is something that we're going to introduce now so that whenever you come up to a polynomial that does not factor, we know how to do it, okay? And what I have basically here for the rest of the video is a bunch of other worked out examples, and I just want to kind of point out some different things that will come up depending on what kind of example you're working with. So you can see how this one shakes out. I start off the exact same way. I just create my pool of applicants here, and that is going to be this pool over here. I have 8 different candidates for the job. And then the first candidate in that list turned out to be the one that worked here pretty nicely for us. That's just positive 1. So that means I've got a 0 of positive 1, and I can go ahead and start to write out the factorization by writing out x minus 1 corresponding to that 0 of x equals 1. And then the leftovers here, right? So it actually turns out that x squared plus 3x plus 14 is not a polynomial that factors very nicely for us. And so you can see here that what you're going to have to resort to doing is using the quadratic formula, okay? Which should be in your notes somewhere, but just to make it easy, let's just go ahead and write it down real quick. The opposite sign of b plus or minus the square root of b squared minus 4ac all over 2a. If you don't have that in your notes anywhere, then make sure to go ahead and write that down at this time, okay? Because you're going to have some examples like this that turn out to be something that you need to use quadratic formula to solve, and you'll notice what the result is. It's a complex set of solutions here, right? So I is going to be joining the party. You're going to end up with a negative under the square root. In orange there, you could see that I basically just scratched out the negative and put an I out front. That was always how we dealt with a negative under the square root. And then we basically have those 2 complex zeros there in the problem. Okay, so that is a situation that could pop up. Another situation that could pop up is that just depending on the constant and the leading coefficient, your pool of candidates can be huge, okay? And so this is maybe yet another reason why I might discourage you from using that method of just going through your complete list of all the zeros and seeing which ones give you a remainder of 0, right? That's not going to be a very efficient method, okay? So we just go through and find the first candidate that works here in this problem. That is going to be a positive 2. And so that positive 2 gives us this algebraic factor right here, x minus 2, and then the leftovers are what we get after doing the synthetic division. And then this turns out to be one that factors pretty nicely here for us, and we get these 3 zeros of positive 2, positive 3 over 2, and then negative 3, okay? And then here in this last example, I've done this one out here as well. The reason I wanted to show this one to you is because sometimes you have to do 2 rounds of interviews, okay? Because the basic idea here is you come up with your pool of applicants, and then you find the first one that works. So here in this case, that would be positive 2 is the first 0 that works as a 0 for this polynomial. But what you might understand here is that what you end up with is not something that we know how to factor itself. That is a 5-term, 4th-degree polynomial, and we just don't have a lot of tools in our toolbox for being able to factor a polynomial like that. So what that's going to mean is you're going to have to go back to your list of applicants, and you're going to have to repeat that process of continuing to do synthetic division until you find another candidate that gives you a remainder of 0. And so here in this example, if I continue to do that, I find here that negative 3 is going to be something that gives me a remainder of 0 with what I had left over there, okay? And so because I had positive 2 and negative 3 that worked out as zeros for me here, that's why you see in the factored form I've got x minus 2 and x plus 3 separately together with that quotient there that I put there in pink. So that's this guy, okay? And then that pink leftovers, that is something that you can continue to factor by grouping and then setting each one of your factors equal to 0 and solving. You can see that I end up with 2 real zeros, and then I end up with 2 complex zeros. So I have positive I and negative I that show up as solutions when I set that x squared plus 1 equal to 0 and solve, okay? So just a couple of subtle nuances that'll pop up when you do problems like these, just some things that I want you to be aware of. Again, you could find the complete notes in the content library on OneNote, but that's all I have for this video. If you guys have any questions whatsoever, then please, as always, feel free to let me know. But thank you very much for your attention, and I will speak to you guys in the next one.